So in this lecture, we're going to talk about molecular representations, so the drawing conventions, isomers, and CH classifications of structures. So our synopsis is basically we're going to look at how structure is communicated in organic chemistry, our key concepts as underlined, and our lecture learning outcomes as highlighted in bold. Upon completion of this lecture, you should be able to do the following: convert a condensed formula to a bond line structure, explain the bonding patterns for hydrogen and carbon and hydrocarbons, classify carbon atoms as primary, secondary, tertiary, or quaternary. Recall that primary is a methyl, secondary is methylene, and tertiary is methine. So those are definitions we need to know. Classify hydrogen atoms as primary, secondary, or tertiary. Draw the possible constitutional isomers for any given molecular formula. Determine if two compounds are constitutional isomers or not. Determine the unique number of carbons in a structure. Determine the unique sets of hydrogens in a structure and the ratio. So we're going to look at the hydrocarbon series, starting from methane going all the way up to hexane in this lecture. And we're going to see how, as we increase the carbon content, how that changes the physical properties of the structure. So let's go ahead and start filling in this table below. As you can see in the first column for the alkane, we have three compounds listed: methane, ethane, propane. So these are called homologs. Basically, we're increasing the CH content as we move down the column. So alkanes are a functional group. They only have carbon and hydrogen. So for methane, the molecular formula is CH4. And what is the molecular weight of that? So let's just do a brief review of Gen Chem, how we figure out molecular weight. We have carbon, we have hydrogen. The atomic mass of carbon is 12. Of hydrogen is 1. So there's 1 carbon, so it's contributing 12. There are 4 hydrogens, that's contributing 4, so we add those. So the molecular weight of methane is 16 grams per mole. So some physical data, and this is just looking up in any sort of resource. The melting point of methane is negative 185 or 182.5. The boiling point is negative 161.5. So we're going to, throughout this course, consider physical properties and how the functional groups influence those in terms of the bulk matter. So at room temperature, the physical state, so if we're considering room temperature to be 25 degrees C, the physical state of methane would be a gas. So in a later lecture, we're going to see how functional groups affect physical state. And again, that's through various intra and intermolecular forces. So again, that's a review of Gen Chem. The condensed formula for methane is going to be written as CH4. The Lewis structure would be the following. So I've drawn a line where we indicate 2 electrons that form a bond. So anytime we see a single bond, again, recall that is 2 electrons. So the bond line structure for methane basically resembles the Lewis structure. So I'll draw it as such. But again, we'll see that it changes when we start looking at the other alkanes in the series. So we've filled out this row for methane, and then we're going to go down the column to ethane, fill out its row, and then we're going to see how adding carbon and hydrogen change the physical properties, and then we'll look at propane. And once we have all those drawn, we're going to go back and look at some other key concepts to understand the learning outcomes 6, 7, and 8 for this lecture. So the molecular formula for ethane, we're increasing the carbon count by 1. So we have C2, and now we have 6 hydrogens. So basically for every carbon we add, we're adding 2 hydrogens, so CH2, that's the increase. So let's just briefly review this, how we calculate molecular formula again, and then after that we'll sort of assume that we know how to do that. Again, carbon contributes 12, hydrogen 1. There's 2 carbons, that's 24. Now there's 6 hydrogens, that's 6, so we're going to add those together. That gets us 30 grams per mole. The melting point of ethane is negative 182, so it's about the same as methane. The boiling point is negative 88.5, so there's a big difference there. So since it's a negative boiling point if we're considering our state at room temp, this is going to be a gas at room temperature. So now the condensed formula for ethane is going to be different than the molecular formula. So this is how it changes from methane. It's basically CH3, CH3. So what you'll notice is that the way a molecular formula is shown, it really tells you nothing about how the atoms are connected. The condensed formula tells you a little bit more, but there's something we have to be aware of when we convert a condensed formula into a Lewis structure. Again, carbon has 4 bonds, hydrogen has 1. If you were to draw out the condensed formula as it's written, you would violate some Lewis rules. So to convert to the Lewis structure, I'm gonna draw a carbon, then I'm gonna bond it to the next carbon. So remember, each carbon has to have 4 bonds. I've shown 1 to each. So we have 6 hydrogens we have to account for. If each carbon needs 3 additional bonds, then each carbon gets 3 hydrogens. So there's the Lewis structure of that condensed formula. So what I meant before, if you literally interpreted the condensed formula as CH3, CH3, you would draw those 3 hydrogens in a line, and that would be wrong because hydrogen can only have 1 bond. So keep that in mind when you convert from a condensed formula to Lewis structure, that you cannot violate any rules of drawing a Lewis dot structure. So now there's a difference between the Lewis structure and the bond line structure. So as you saw me write in the Lewis structure, it can get a little bit unwieldy if you have to draw every hydrogen on every carbon, because we're going to be dealing with some pretty big molecules, and we want to make sure that we're efficient in drawing them. So in a bond line structure, the hydrogens that are bonded to carbon are implicit, meaning they are there, we are just not drawing them. And that another thing, we're not going to actually draw the letter C, we're actually just going to draw a line. So for ethane, the bond line formula would just be the following. Just a simple what looks like a bond. But basically at the two ends of that line, it is assumed each of those is a carbon atom, and because we're only showing one bond, each of those has 3 implicit hydrogen atoms present. Let's move on to propane, and then you'll see how the bond line structure makes sense in conveying structure in a very efficient fashion. So we're increasing the homolog count here by CH2. So now we have C3H8. If we take 12 times 3, that's 36. 1 times 8, that's 8. So we're going to get 44 grams per mole. So again, if you look at sort of the change in molecular weight in going up the series, each of the molecular weights differs by 14 grams per mole, and that's equivalent of CH2. So the melting point of propane is negative 187.7. The boiling point is negative 42.3. So you see the melting points going down that series are all pretty much the same. The boiling points, though, change quite a bit. So we're still, if in our standard state, at room temp, 25 degrees C, propane would be a gas. What is the condensed formula? So now we have CH3, CH2, CH3. And we're going to convert that to a Lewis dot structure. Plug in the rest of our hydrogens. So as you can see in this trend, every carbon has 4 bonds, every hydrogen has 1 bond. So we have 3 carbons in the backbone. So how do we convert the Lewis structure to the bond line structure? So right there, that's 2 carbons. We draw the last one, so that's 3. So now you can see that when the 2 lines intersect at that vertex, that is a carbon as well. So that bond line structure is showing you 3 carbons and 8 hydrogens. So at this point, before we move on, I want to introduce how we can classify carbon atoms and hydrogen atoms, and how we look at symmetry in a structure. So if we look at methane, there's 1 carbon, there's 4 hydrogens. The hydrogens are all the same type. So we can basically say there is 1 type of carbon and there's 1 type of hydrogen. If we look at ethane, we can see that that's the same as well. We have CH3, CH3. Both the carbons are of the same type. So we have 1 type carbon and we have 1 type of hydrogen. So a CH3 group, so we have CH3, CH3. A CH3 group is called a methyl group. And because the carbon of a methyl group is only bonded to one other carbon, we call that a primary carbon. So a methyl group is primary. The hydrogens of a methyl group are also called primary hydrogens. So let's go through propane, and you'll see how we have different types of carbon and different types of hydrogen. So when we inserted that CH2 group into the alkane of propane, we've created a different type of carbon. So you can see we have two CH3 groups, and then we have a CH2 group. The CH3 groups are the same type. The CH2 group is different, so we have two types of carbon now. And we said before that CH3 groups are called methyl groups. A CH2 group has to be called something different because it's not the same. And it's actually called methylene. So we have two types of carbon. We have, if we look, therefore, two types of hydrogen. We have CH3 type hydrogens, and we have CH2. So if we classify the ratio of the methyl hydrogens to the methylene, we're simply counting them. We have 6 of the methyl to 2 of the methylene. So now if we add that together, 6 plus 2 is 8. And what you can see from our molecular formula, we have 8 hydrogens total. And so all we're doing is we're counting the hydrogens and we're classifying them. But what about this carbon number here? The molecular formula has 3 carbons, but there's only 2 types. And why is that? That's due to symmetry. So one way to think about the structure, and I'll go to the bond line structure, is that there's a mirror plane in the molecule. So you can see if I draw this dotted line down the center carbon, and you imagine that as a mirror plane, these 2 carbons mirror one another. So if I were to draw basically a dot, and then the central carbon as a square, so you can see that, using that sort of shape analysis, the terminal carbons mirror each other, so they're the same type. The central carbon is different, so I gave it a different shape. It's just completely arbitrary. So there's 2 types of carbon. And so what we're saying is that while the molecular formula has 3 carbons in it, there are only 2 different types of carbon. So what I'd like to do next is continue in the series of alkanes by going up 1 to butane. So we have a name butane. And again, if you look at this functional group, alkane, A-N-E, this name butane, B-U-T-A-N-E, we're going to find that as we learn nomenclature in organic chemistry, the suffix of a name indicates the major functional group that's present. So alkanes are hydrocarbons, meaning that they only have carbons and hydrogens. There's no other sorts of elements in the structure. So our molecular formula, C4H10. So 12 times 4 is 48, plus 1 times 10 is 10. So we add those together, we get 58 grams per mole. The melting point of butane is negative 140 degrees C. The boiling point is negative 1. So we're encroaching now room temperature at 25 degrees C, but this is still a gas. So what is the condensed formula? We have CH3, CH2, CH2, CH3. So at this point you can see if we're going to draw the Lewis structure of that, it's going to get pretty crazy because we got a lot of CH's in there. So we're going to basically just transition to communicating everything through a bond line formula. So I'm going to draw 2 carbons. Here's the third, and then there's the fourth. So by looking at the bond line formula, if you think of what you should be able to do, if you're given that bond line formula, you should be able to count the number of carbons, count the number of hydrogens to determine the molecular formula. From the molecular formula, determine the molecular weight. And then we're going to continue on with our exercise of classifying the types of carbons and types of hydrogens in the molecule. So let me put some numbers. I'm just going to number this bond line formula chain. So 1, 2, 3, 4. And if we consider that carbons 1 and 4 are both methyl groups, CH3, they are the same type of carbon. Carbons 2 and 3 are methylene, CH2 groups. They're the same type due to symmetry. And where is the symmetry element? It basically bisects carbons 2 and 3. So 1 and 4 are the same, 2 and 3 are the same. That leaves us with 2 types of carbon. And so it's going to mirror the hydrogen as well. So we're going to have 2 types of hydrogen. So maybe what I can show you is the ratio now. Again, keep in mind carbons 1 and 4 are methyl groups. They each have 3 hydrogens, so that's a total of 6. Carbons 2 and 3 are methylene. They each have 2 hydrogens, so that's 4. So if we add that together, that gets us 10. And again, that matches what we see in the molecular formula. However, carbons, we have 2. The molecular formula has 4. So what that means when the types of carbon are less than what you see in the molecular formula, that's telling you the molecule has some form of symmetry. And we're gonna look at symmetry as an important element in this course as we progress through these different topics. So it turns out for the molecular formula of C4H10, butane is not the only structure that exists. We can actually combine all of those carbon and hydrogen atoms in a different manner that gives a different compound. So what I'm going to do now is just basically I'm going to go through, as we've done before, filling the row out from left to right. And as we move up to higher count of carbon, we'll approach this problem a little bit differently. So my goal here is to expose you to ways of thinking about this to help you solve problems. So right now I'm just going to give you the information, and as we progress through this, we'll think about it a little bit different. So I said C4H10 has another structure. The name of that structure is the following. 2-methylpropane. So as a preview of nomenclature, again, we said that when the functional group ends in ane, it's an alkane. We already saw that propane was a 3-carbon count molecule. So maybe what I can do over in the bond line column now is draw propane. So that's propane. Let me put in numbers. I want to number the carbons, 1, 2, 3. So to accurately draw the structure from this name, we've drawn propane. Now it says at the 2 position there's a methyl group. And we said that methyl was CH3. So if we put a bond at the 2 position, we're basically now putting that methyl group in. So when you look at that bond line structure and you see the 3-carbon chain, and at the 2 position there's a methyl group, we've just drawn 2-methylpropane. How do we put that in terms of a condensed formula at this point? So one way we can do that, if we're looking at carbons 1, 2, and 3, we can do as we've done before, and we can have the 2-position methyl group hang off in terms of a bond. So let's go ahead and fill in the rest of the columns, and we'll get to our types of C and H's. Again, since they have the same molecular formula, they have the same molecular weight. So that right there presents to us an issue. If you have a compound with the same molecular formula and same molecular weight, how do you know they are different? And through classifying the types of C and H, that's how we differentiate them. We can also use physical properties. So the melting point of 2-methylpropane is -159. The boiling point is -11.7, and therefore this is a gas. So we can see by the melting and boiling points they're different. But also now let's consider the types of C and H. We'll see that they're different as well. So when we're looking at 2-methylpropane, we can see that now there are 2 unique types of carbon. And what I'm going to do is just put like a red dot. So here's a methyl group, here's a methyl group, and there's a methyl group. Those are all the same type. Carbon 2 is then different. I'm going to do a little red square. So we have 2 types. So that doesn't differentiate from butane. But we'll see that the types of hydrogens do. So again, the the red circles and the red squares. The circles are all the same type of hydrogen. That's 2 types. The ratio of the circles to the squares, if we count, the methyl groups each have 3. There's 3 of them, so that's 9. The square is 1. Now if we add that, we still get 10, and that's what matches the molecular formula. So again, the ratio should always equal what you see in the molecular formula when you sum them. But you can see that they're different between butane, it's 6-4, and 2-methylpropane is 9-1. So just with this thought exercise, we've differentiated the structures. So one other important thing I'd like to point out about these 2 molecules. Butane itself is what we call or classify as a linear molecule. The 2-methylpropane is what we call branched. And so you can see that sort of makes sense. All the carbons are in a line for the linear structure, and then the branch structure you have at the 2 position, it's branching off. So on this same slide, I'd like to continue on increasing the carbon count to the next highest one, which is called pentane. Pentane has the molecular formula C5H12. So you can see that as we increase, we are adding a CH2 group. And again, that corresponds to 14 grams per mole, so 58 plus 14, that gets us 72 grams per mole. The melting point of pentane is negative 130.5. The boiling point is 35.9. So if we're sitting at 25 degrees and the boiling point is 35.9, this is now a liquid at room temperature. So let's go ahead and draw the condensed formula. So we've drawn the 5 carbons. We've given each of those the appropriate number of hydrogens. Let's draw the bond line. Let's go ahead and number that now. So 1, 2, 3, 4, 5. So let's from this determine the unique types of C and the unique types of H in the ratio of those H sets. So if I can, I'm just going to use this sort of system to say that those methyl groups, CH3 group is methyl, are the same. Now, if you look internally to that, the internal carbons, if the methyl groups are at the terminus, the CH2 groups are internal carbons, so the methylene groups. Even though they are all CH2, they are not all the same, they're different. Those are the same, but then this internal one is different from the outer ones. So what this is telling us is we have 3 types of carbon. We have methyl, and then we have 2 types of methylene. In this case, the types of hydrogen also are the same. We have 3 types of hydrogen. The ratio, the methyl groups, we have 3 and 3, so that's 6. Then we have methylene. We have 2 types of methylene. We have 4 and 2. So again, when we sum that, that gets us 12, which we observe in the molecular formula. So the fact that we have 3 types of carbon, the molecular formula has 5, means there's symmetry. And basically the symmetry is bisecting carbon 3. So what's another way to rationalize that? So 1 is equal to 5, 2 is equal to 4, and then there's 3. So this gets us our basically, if we look at this, this is our 3 types of carbon. Analogously, the 3 types of H, and then the ratio between them. So if we're considering that, as we saw with the C4H10, what about the molecular formula C5H12? Is there any other way we can connect all these atoms present? So C5H12 again, yes there is. Again, that's 72. Now the logic in this is the first compound that we drew is linear. Any subsequent compounds we propose must be branched. So this next compound must be branched. And the reason it must be branched is because we've already used all 5 carbons in a straight chain. So therefore, what we're going to do in a logical fashion, instead of starting with a C5 chain, we're going to go ahead and draw a C4 chain. So tying these concepts together, the name of this compound, if it's a C4 chain, it has to be a butane. It's a butane derivative. So we've accounted for 4 carbons. We have a 5th carbon we have to place on that chain. We cannot place it at carbon 1 or 4 because that's just going to make the pentane chain. So therefore we can place it at carbon 2. I'm going to show you that if you place it at carbon 3, you're still drawing the same thing. The numbers of the chain are just reversed. One, 2, 3, 4. So we've put a methyl group at carbon 2, so this is 2-methylbutane. So what's the melting point of 2-methylbutane? -161. The boiling point, 27.8. It's slightly above room temperature, so this is a liquid. So how can we draw the condensed formula for that? So what I've done is, we see that carbon 2 has 2 methyl groups on it. Those methyl groups are the same type of methyl group. So I've just condensed them into a parentheses, put a 2. Carbon 2 is what we call a methine carbon. It has 3 carbon bonds, 1 H bond. So we have methyl, methylene, methine. So let me point that out. This is called a methine. Methine carbon or a tertiary carbon. Again, that means a carbon atom bonded to 3 other carbon atoms. A CH2, which is a methylene, and then another methyl group. So let me just use these dots. So this methyl group and that methyl group are the same. So that's one unique type of carbon. The methyl group at carbon 4 is not the same type. Then we have the methylene, which is obviously different. So I use a little triangle. And then the methine at C2, I'll put a little asterisk. So if we count those different shapes, we have 4 different shapes. So that's 4 unique carbon. The same thing goes for the hydrogens. Those map on pretty straightforward. We have 4 unique type of hydrogen. So the circles, those are methyls. There's 6 total hydrogen. The square at 4, that's a methyl, that's 3 hydrogens. The triangle at 3, that's 2 hydrogens. And then the asterisk at carbon 2, that's 1. So again, we sum that all together. 6 plus 3 is 9. Plus 2 is 11, plus 1, that's 12. And again, that equals 12. And the number of carbons, 4, is less than 5. The symmetry, again, is because the groups bonded to C2, those methyl groups are equivalent. So the relationship between pentane and 2-methylbutane, we call these constitutional isomers. A constitutional isomer has the same molecular formula, the same molecular weight, but different connectivities of the atoms involved. So in the next exercise, we're going to go up one more carbon atom, one more CH2 group basically, to the C6. So the name of the linear compound is called hexane. This is C6H14. So what I'm going to do now is I'm going to draw the bond line formula. We're not going to draw the condensed formula anymore, just so that we can communicate the structure a little bit faster. So we said that for the parent compound will always be linear. So let's count these carbons. We have 1, 2, 3, 4, 5, 6. So that gets us a molecular weight of 86 for this molecular formula. And we're going to see that hexane now has quite a number of constitutional isomers associated with it. Again, if this is linear, the remaining ones have to be branched. So what I want to do now is just basically go through figuring out what those isomers are. Then we'll name them, and we'll then circle back, determine the unique sets of each and how they're all differentiated. So if the remaining ones have to be branched, when we can no longer start with a C6 chain, we have to start with C5. So we number that 1, 2, 3, 4, 5. So we're missing a carbon atom and the associated hydrogen atom. So let's do this in a very logical fashion. Again, we can't put it at positions 1 or 5 because we're just remaking the linear compound. Let's put it at position 2. So that's a methyl group at position 2. So what we've made, 2-methyl, and the chain here now is a pentane. 2-methyl pentane. Again, that's the same molecular formula, same molecular weight. These are constitutional isomers. So you might ask, well, you put the methyl group at C2, what about putting it at C3? That's certainly viable as well. So now the methyl group is at C3, so this is a different compound. This is 3-methyl pentane. Has the same molecular formula, same molecular weight. So we went from linear to branched. Can we go any further? Yes, we can. We cannot go any further with pentane, so we have to basically start with the next size down carbon chain, that's C4. One, two, three, 4. Now this is going to be a butane derivative. Now we have 2 methyl groups to account for. And again, when you're doing this exercise, you can never put them at the terminus because then you'd be creating a compound you already made. So let's go ahead and put them. There's one at C2. Let's put the other one at C2. So we put both those methyl groups at carbon 2. So basically we've made 2,2-dimethyl butane. This is C6H14, same molecular weight, 86. So all of these compounds now are constitutional isomers. But we have one more to go, because remember we put the methyl groups at both at 2. Let's draw our C4 chain again. Let's put one at 2 and one at 3. So now this is a new compound. The bonding pattern is different. This is 2,3-dimethylbutane. Molecular formula is the same, C6H14. The molecular weight's the same. So all of these are constitutional isomers. So what we want to be cognizant of is that if you are given a molecular formula, from the molecular formula alone, you really do not know how the atoms are connected. And so the exercise we just did was figuring out how they are. So what we can do now is differentiate them using the unique type of carbon and unique type of hydrogen. And so that's useful to us to actually identifying which compound is which. So let's go through our exercise. For hexane, the unique type of carbon. So 1 and 6 are the same. 2, 3, 4, and 5 are all CH2 groups, but they're not all equivalent to one another. 2 and 5 are, and 3 and 4 are. So total, that gets us 3 unique types of carbon. So maybe we can analyze the hydrogen atoms using different terminology. So 1 and 6 are methyl groups, and so I'm going to call them their primary. 2 and 4 are secondary, 2 and 5, and 3 and 4 are secondary. So now you can look at that structure and say a methyl group, CH3 is primary, a methylene group, CH2 is secondary. So 2, 3, 4, and 5, just like with the carbons, are not all equivalent. Two is equal to 5, 3 is equal to 4. So we have the same scenario for the hydrogens. And if we look at those ratios, we can see that it's the methyl groups, there's 6. The 2 and the 5, there's 4. The 3 and the 4, there's 4 as well. So that's getting us 14 total hydrogens. So to clean that up a little bit, maybe I can just draw this. I can say there's 3 unique type of carbon, 3 unique type of hydrogen. The ratio of those is 6 to 4 to 4. So that sequence of numbers sort of describes that structure, that constitutional isomer. So how does 2-methylpentane differ? So let's use this classification. We have a primary, carbon 2 now is tertiary, 3 secondary, 4 is secondary, 5 is primary. So the methyl groups bound to carbon 2 are equivalent to one another. So that's one type of carbon. Carbon 2 is its own thing because it's a methine or tertiary carbon. Carbons 3 and 4, while they're both CH2 groups, are different types because they are bonded to different things. So that gets us up to 4 different types of carbon. And then the methyl group at C5 is primary, but it's different from the primary carbons that we've classified before because it's in a different bonding arrangement. So we have in this this constitutional isomer, we have 5 unique type of carbon. The same analysis holds true for the type of hydrogen. There's 5. The ratio of those, and I'm just going to go in descending order. We have the methyl groups, 3 plus 3 is 6. The other methyl group at 5, that's 3. The methylene groups at 3 and 4, so 2, 2, and then the methine at carbon 2 is 1, And again, that gets 14. So why is this type of thought process useful to us? If you look for hexane, this is what we determined. That was the unique type of C and H in the ratio. Now what we've determined here is different. So we've used a thought process of classification to differentiate these constitutional isomers, again, that have the same molecular formula. Running through this analysis again, we have 3-methyl pentane. In this one, we can actually see a mirror plane. I'm going to draw it down. Here we see that carbons 1 and 5 mirror each other. 2 and 4 mirror each other. 3 is unique. And then the methyl group bound to C3 is unique as well. So that gets us 4 unique type of carbon. One and 5 hydrogens are the same. 2 and 4 are the same. 3 is unique. And then the methyl group at C3 is unique. So this is also 4. So if we determine that ratio, again, I'm just going to go from highest to lowest. We have 6 to 4 to 3 to 1. And again, that gets us 14. And again, that is, again, different from the 2 prior constitutional isomers that we determined. For 2,2-dimethylbutane, what I want to do now is use some shapes with the blue color to show you that all the methyl groups bound to carbon 2 are the same. So those are all the same type of carbon. They're all methyl groups, primary. You have another methyl group at 4, but that's different. Then you have a CH2 group at 3. Now carbon 2 does not have any hydrogens, but it's different. So that gets us 4 unique type of carbon. Now, because carbon 2 did not have hydrogen, the total unique sets of hydrogens is 1 less. So the blue circles, those are all methyl type hydrogens. The methyl at C4, that's a different type. The methylene at C3, that's its own type. So that's 3 types. We can determine that ratio now. We have 3 methyl groups, each with 3 hydrogens. We have a methyl group at C4, that's 3. And then the methylene at C3, that's 2. So again, that equals 14. So you can see that that's completely different than all the other constitutional isomers we determined. And then finally for 2,3-dimethylbutane, we basically have only 2 types of carbon. All the methyl groups now are equivalent. And so why is that? This actually has 2 different types of symmetry. We have a symmetric plane here and a symmetric plane there. So meaning that these CH2, the CH groups at 2 and 3, that's the other type of carbon. You have methyl groups and you have methine groups. Similarly for hydrogen, there's 2 sets. And the ratio of those are 3, 6, 9, 12. 12 methyl type hydrogens to 2 methine type hydrogens. And so we see that that's also different. So what are we really doing with this uniqueness test? Why are we figuring this out? This actually relates to what we're going to be doing in Module 2. When we study spectroscopy. Really what we've done in this thought exercise is the core concept of interpreting spectral data, specifically nuclear magnetic resonance spectral data. When we look at carbon-13 data, we're going to look for unique types of carbon. When we look at proton NMR data, we're going to look at unique types of hydrogens. So let's fill out the rest of this table with the melting and boiling points, just so we can see some more trends. Hexane melts at -96 and it boils at 68.5, so it is a liquid at room temperature. 2-methylpentane, now we've started to branch. It melts at -60 and it boils at 60, so this is a liquid. 3-methylpentane melts at -62, boils at 62.9, so therefore it is a liquid as well. 2,2-dimethylbutane melts at -102, boils at 49.7, it's also a liquid. 2,3-dimethylbutane melts at -136, boils at 57.9, so it's also a liquid. So between the linear and the branched, so if we were specifically looking at, say, this number here, the boiling point for hexane versus the boiling point for 2,3-dimethylbutane. One thing we could sort of think about in terms of three-dimensional shape, hexane is linear, so this is sort of spaghetti-like. The 2,2-dimethylbutane is branched, so the branching sort of makes it M&M-like the candy. So if you think about spaghetti molecules all intertangling with one another, you know, when something boils, the molecules have to get away from one another. And if they're intertangled, that's a little bit harder to do. With the 2,2-dimethylbutane, you know, the molecules are more compact, and so they're not really entangled with one another as much as a linear molecule would be. So the contact between them is less. There's less surface area touching, so it's a little bit easier to boil. So that's sort of a qualitative understanding of how shape impacts a physical property. It's not something you would say 100% happens all the time. So this has been a lecture on looking at the alkane functional groups, converting a molecular formula into a Lewis structure, drawing a bond line formula, understanding that constitutional isomers can exist for different molecular formulas, and using the concept of uniqueness to differentiate the constitutional isomers.